Hello everyone. Today we're going to be exploring a fundamental concept in geometry, and that is proving triangle congruence using specific theorems. So by the end of this lesson, you'll be able to use the side-side-side congruence theorem, the side-angle-side congruence theorem, which we've already learned, the angle-side-angle theorem, the angle-angle-side theorem, and the hypotenuse-leg theorem to solve problems involving triangles. So first of all, we want to recall what it means for triangles to be congruent. So two triangles are congruent if all their corresponding sides and angles are equal. Essentially, they're the same shape. They're identical in shape and size, even if their orientation or position is different. However, checking all 6 pairs of corresponding parts can be time-consuming. That's where our congruence theorems come in handy. They allow us to prove triangle congruence by only verifying certain parts of the triangle. So in these 3 triangles to our right here, these 2 triangles are congruent. They're the same shape. They have all the same angles on the inside. It's just that their orientation and position is a little different. Whereas this third one is obviously not the same shape. It has different side lengths and different angles. So the first theorem we're going to talk about is the side-side-side congruence theorem. And the SSS theorem states that if 3 sides of one triangle are congruent to 3 sides of another triangle, then the triangles are congruent. So this theorem works because fixing the lengths of all 3 sides determines a unique triangle. And this is definitely the most intuitive of the theorems. Yeah, if all 3 sides of a triangle are the same length, then those 2 triangles have to be congruent to each other by the definition of congruence. Next up is the angle-side-angle congruence theorem. And the ASA theorem states that if 2 angles and the included side of one triangle are congruent to 2 angles and the included side of another triangle, then the triangles have to be congruent. Now, I highlight the importance of the included side. That means the side that's between the angles. In this case, side AC and side DF on these 2 triangles in the diagram here. The included side has to be between the 2 angles that you know are congruent for you to use the angle-side-angle congruence theorem. Next up, we have the angle-angle-side congruence theorem. And the AAS theorem states that if 2 angles and a non-included side of one triangle are congruent to 2 angles and a non-included side of another triangle, then the 2 triangles are congruent. So non-included side, in this case, means the side that is not between those 2 angles, or a side that is not directly between those 2 angles. And even though the side is not between the 2 angles, knowing that 2 angles of one triangle are congruent to 2 angles of the other triangle allow us to determine that third angle, because all of the angles of a triangle add up to 180 degrees. So really, the angle-angle-side congruence theorem is just kind of one step removed from the angle-side-angle congruence theorem. And then finally, the last new theorem we'll learn about today is the hypotenuse-leg theorem for right triangles. The HL theorem states that if the hypotenuse and one leg of a right triangle are congruent to the hypotenuse and one leg of another right triangle, then the 2 triangles are congruent. However, very important note here that this theorem, the hypotenuse-leg theorem, only applies to right triangles. You can only use this theorem if you know that there is a right angle in the triangle. So in the case of these 2 triangles in the diagram here, we know that angle C is a right angle, and we know that angle J is a right angle, and we know that one of the legs and the hypotenuses of both of the triangles are congruent, which means we can say, based on the HL theorem, that triangle ABC is congruent to triangle GHJ. So a little bit about why these theorems work. Understanding why they're valid helps reinforce, their importance and why we can use them the way that we do. So the SSS theorem is pretty intuitive. 3 sides fix the triangle shape completely. If all the sides are the same, then they have to be congruent. The angle-side-angle theorem, well, 2 angles in the included side ensure that the third angle of that triangle and the other 2 sides are determined by the ones that you already know. For all of these theorems, we could theoretically solve for all of the rest of the angles on the sides, or at the very least prove that they are congruent based on these theorems. But these theorems are basically like a shortcut saying, well, we don't have to do that. Likewise, the angle-angle-side theorem, knowing 2 angles allows us to find the third angle, and then the side fixes the triangle's size. So if you only knew that all 3 angles were congruent on a triangle, one triangle could still be larger or smaller than the other one, but having a congruent side fixes the triangle's shape so where they must be congruent. And finally, the hypotenuse-leg theorem. In right triangles, the right angle and the hypotenuse-leg combination uniquely determine the triangle. So, in this first example, the question asks us, by which theorem can we prove the triangles are congruent? And if we examine the diagram here, we have a set of corresponding congruent angles, M and P. We have a set of corresponding congruent sides, MN and PQ. And let's write this down. We know that angle M is congruent to angle P. We know that side MN is congruent to side PQ. And we know that angle N is congruent to angle Q. And it asks us, by which theorem can we prove the triangles are congruent? Well, let's look at what we have here. We have an angle, we have a side, and we have an angle that are congruent. And that side is between, it is the included side between those 2 angles. So we can use the ASA theorem to prove that those 2 triangles are congruent. So we can say that triangle MNO is congruent to triangle PQR by the angle-side-angle ASA Congruence Theorem. A lot of these questions are just going to be about identifying what the problem gives you. If you can identify the elements that are the same in each triangle, then you'll be able to figure out which theorem to use. All right, in example 2 here, we have, it asks us again to ask which theorem we can use to prove that the 2 triangles are congruent. And we have 3 pairs of corresponding congruent sides. GH congruent to JK, HI congruent to KL, and GI congruent to JL. This is a pretty standard case of side congruence theorem. So we can say that triangle GHI is congruent to triangle JKL by the SSS Congruence Theorem. And finally, in the third example here, we are given that right triangles STU and VWX with right triangles at angle T and angle W. And as you can see, we don't have a fully fleshed out diagram, so let's go ahead and label what we are given in the problem. They tell us that there are right triangles STU and VWX with the right angles at T and W. Let's mark the right angles, T and W. And now let's fill in the rest of the vertices so we can put our S and our V on the top and our U and our X as the remaining vertex. And they also tell us that T and W are right angles. They tell us that the hypotenuse SU is congruent to the hypotenuse VX. We'll mark those two congruent. And they tell us that the leg TU is congruent to the leg WX. So the bottom of our first triangle is congruent to the bottom leg of our second triangle. And it asks by which theorem we can prove the triangles are congruent. This is a classic case of the hypotenuse-leg theorem at work. Again, remember the HL theorem only works for right triangles, but since we have a right triangle with the hypotenuses congruent and one of the corresponding legs congruent, then we can conclude by the HL theorem that triangle STU and triangle VWX are congruent. I want to make a note here that it's very important that you list those vertices in the correct order, because the order in which you list them corresponds with what parts of the triangle are congruent to each other. Angle S is congruent to angle V, so they need to be the first vertices listed whenever you list those triangles, whenever you name those triangles. All right, we're going to get started with a couple practice problems here. And for these, you're going to need to draw the given information on the diagram yourself, and then come up with your own conclusion. In this case, we want to prove that the two triangles are congruent, and you'll have to justify your answer using one of the theorems we've learned about in this lesson. So, give that a shot, and then we'll go over the answer in just a second. You can pause the video. Ready? Okay. So, we have triangle ABC and triangle DEF. So let's label A, B, C, and then remember, in the same corresponding spots on the second triangle, we're going to put D, E, and F. They tell us that side AB is congruent to side DE. They tell us that side BC is congruent to side EF. And they tell us that side AC is congruent to side DF. Well, since all three pairs of corresponding sides are congruent, then triangle ABC is congruent to triangle DEF by the side congruence theorem. Starting off nice and simple. On the second practice problem here, we're given that triangle GHI and triangle JKL have the following characteristics: that angle G is congruent to angle J, that side GH is congruent to side JK, and that angle H is congruent to angle K. So again, let's go ahead and label the information we are given. These Diagram triangles are really just placeholders. We don't actually know what the triangles look like, whether the angles represented are in any way close to the angles that are present on these triangles, but they're just a placeholder for us to visualize the problem. So we have triangle GHI, and again in the same corresponding spots, triangle JKL. It tells us that angle G is congruent to angle J. We'll put one arc through each of those. That side GH is congruent to side JK. We'll put one mark through those to say that those are congruent. And that angle H is congruent to angle K. We'll put two little arcs through those angles to denote that they are congruent. So with our diagram fully built, our task is to prove that the two triangles are congruent. Go ahead and get your answer. Write down your answer on a piece of paper or answer the question in the video. And we'll go over the answer in just a second. So we want to prove the two triangles are congruent. Well, we have an angle, a side, and an angle. And the side, since it is included between those two angles, allows us to prove that triangle GHI is congruent to triangle JKL by the angle, side, angle. Again, angle, side, angle, congruence theorem. All right, in practice number 3 here, we have triangle MNO and triangle PQR, which are right triangles with right angles at N and Q respectively. It tells us that the hypotenuse side MO is congruent to side PR, and that leg NO is congruent to leg QR. Our task is to prove that the two triangles are congruent. So go ahead and label your diagrams on your paper, and then we can go ahead and solve the problem. Ready? Okay. We have triangle M, N, O, and triangle P, Q, R. We have right angles at angle N and angle Q. It tells us that the hypotenuse MO is congruent to the hypotenuse PR, and that leg NO is congruent to leg QR. Therefore, we have a hypotenuse and a leg of a right triangle that are congruent in each case. So by the HL theorem, triangle MNO is congruent to triangle PQR. Right, a couple more practice problems. We get a little more complicated now. The question asks us, can the triangles be proven congruent with the information given in the diagram? If so, state the theorem you can use. Give this a shot and we'll go over the answer in just 1 second. Ready? Okay. So we have two triangles. We have FEG and DHG. We know, for example, that angle H is congruent to angle E because they are both right angles, but we actually have to include one more piece of information so that we can prove that these two triangles are congruent. We know that vertical angles are congruent. So we can say that these two angles formed by opposite angles formed by intersecting lines are congruent. That lets us prove that if we have an angle and a side, a non-included side, congruent to an angle and a non-included side of another triangle, then the two triangles must be congruent by the angle-side theorem. So to write that out formally, triangle, we'll go with GEF is congruent to triangle GHD by the angle-side congruence theorem. And again, that's because angle H is congruent to angle E, angle G, and actually, we can't just say angle G because angle G is involved in multiple angles. So we would say angle DGH is congruent to angle FGE. And finally, the problem gave us that side FG was congruent to side DG. That's an angle, and a non-included side. So we can use the AAS Congruence Theorem. In this next practice problem, the problem asks us, again, can the triangles be proven congruent with the information given in the diagram? If so, state the theorem you can use. And this is a bit of a tricky one, so take your time, answer it real quick, and we'll go over the answer in just a second. Ready? Okay. So, we know that the larger all-encompassing triangle, PQR, we know that it's isosceles because it has two sides that are the same length. And based on the fact that it is isosceles, like we learned about in a previous lesson, we know that the base angles of isosceles triangles are congruent. So we can add that in. We can add that angle P and angle R are congruent. We also know that this segment in the middle, because of the reflexive property, is always going to be congruent to itself. So we know that QM is always going to be congruent to, well, itself, QM. And that is all of the information we can glean from this problem. Question is it going to be enough to use any of our theorems to state that these two triangles, PQM and RQM, are congruent? Well, let's go through the list. We have side, 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 angle, side, angle, angle, side, angle, side, angle, and hypotenuse-leg. Right off the bat, we do not see any right angles in this problem. So, hypotenuse-leg is out. We also cannot conclusively say that side PM and side RM are congruent, which means that we can't say that all three sides are congruent. So we're left with side, angle, side, angle, angle, side, or angle, side, angle. Well, if we were going to use side, angle, side, then we would have to know that the angles, the included angle between our congruent sides, were also congruent. We don't know anything about these two angles at the top of these triangles, so we cannot use side, angle, side. We also don't know two angles. We only know that one pair of angles is congruent, so we can't use angle, angle, side. So our last hope is angle, side, angle. And again, there are two angles required for angle, side, angle. We only know one pair of angles. So we have exhausted all of the possibilities that we know to prove that these two triangles are congruent. So no, we cannot prove the triangles are congruent using the given information. We would have to know some other piece of information about these triangles to conclusively say that those two triangles are congruent, and we don't have that. And finally, the last practice problem here. Again, can the triangles be proven congruent with the information given in the diagram? If so, state the theorem you can use. So we have triangle LMP and triangle NMP. And question asks us, are they congruent? If so, state the theorem you can use. Give it a shot. We'll go over the answer in just a second. Ready? Okay. So we know two angles of these, two corresponding congruent angles of the triangles. We know that angle LMP is congruent to angle NMP. And we know that angle LPM is congruent to angle NPM. But right in between those two angles, there's a side, isn't there? There's this side that was where both of the triangles touch. It is the same segment, ME. And by the reflexive property of congruence, segment MP is always going to be congruent to itself. So side MP is always congruent to side MP. This gives us an angle, a side, and an angle of each triangle that we know are congruent, and the side that is congruent is included between the two angles. So we can say that triangle LMP is congruent to triangle NMP by the angle, side, angle congruence theorem. So that is the end of the lesson for today. Understanding and applying these theorems simplifies the process of proving the triangles are congruent, and they're powerful tools in solving geometric problems efficiently, so that we don't have to find all of the side lengths of a triangle. As long as we can identify certain elements of two triangles are congruent to each other, that is enough to prove that the triangles as a whole are congruent. Feel free to ask me any questions, and we'll see you in the next lesson. Bye-bye.